Now the other thing that we do with our differentiating is we use it to help us when we're curve sketching. So I've got two examples, an easier one and a harder one. This first one we need to sketch y equals sine x plus cos x, and we're given the domain. It's only between 0 and 2 pi. Now we've got our curve sketching menu. Please do support ISA children. And some of these steps are really useful and kind of essential for graphing some functions, and others we can sort of leave out. For example, there's nothing really we need to do to prepare this, so we can pretty much leave that. We're also unlikely to be finding any asymptotes in one of these sorts of curves because we know the nature of y equals sine x goes on forever and y equals cos x goes on forever. So if we're adding these two together, that idea of a composite function that's going to be somewhat reminiscent of both of these curves should be in our heads. Now the domain is something we don't need to consider either because we've been told the domain, so there's no point thinking that through. The symmetry, well, not a bad idea to think about symmetry. We know that y equals sine x is an odd function and y equals cos x is an even function, so thinking through what happens there might be important sometimes. Will it be important this time though? No, because we're only sketching on the right-hand side of the y-axis here, so thinking about what's going on the other side is probably a bit of a waste of time. And we want to save time when we do these sorts of questions so that we can get on to other questions and not get bogged down. So really, we need to think about intercepts. We could think about the sign of the function, I suppose, but using our calculus to find high points and low points and points of inflection is probably going to be one of the most helpful things. Another thing that's not actually on there, that's going to be something I'm going to start with, is I'm interested in what point my curve sits on when x is 0 and when x is 2 pi, because if I've got that, I've got my endpoints, and that's what helps me know what might be happening in between. So I'm going to start with that, literally just because it gives me something I can draw. I'm going to draw up my graph so that I've got something to go with. Let's make that 2 pi. So this can be pi. Let's put in pi on 2 and 3 pi on 2 because they're likely to be important points. We can put little markers for the quarters of pi's in there. And now let's think through when x equals 0, what's y? Because here, effectively, we are doing this as a first step. We're finding an intercept. This is going to be an intercept over here. All right, well, when x equals 0, we've got the sine of 0 plus the cos of 0. Now, I know my sine curve and my cos curve quite well, but just having a simple sketch of each one of them. Here's sine, and here's cos. Over that same domain of 2 pi, it helps me answer some of these questions quite quickly and easily. So when x is 0, sine of 0 is 0, and the cos of 0 is 1. So clearly, my sketch is going to start at 1. So I'm going to put that on nice and confidently as a dot. All right, what about when x equals 2 pi? Well, when x equals 2 pi, I've got y equals the sine of 2 pi plus the cos of 2 pi. Now, I know straight away that whatever my sine curve is doing when x is 0, it's doing the same thing at 2 pi, and so is this one. So it's going to be the exact same. So if I'm starting at 1, I'm also finishing at 1, so I can put that in as well. Let's have a look now for our x-intercepts. So to do that, we have to let y equal 0. So let y equal 0, we have 0 equals sine x plus cos x. Now there's a few ways to solve this. I'm going to choose to subtract cos x from both sides. So I have it like this, and I know in my head that sine x divided by cos x equals tan x. So I can divide both sides now by cos x. This side will be minus 1, and this side will be tan of x. In other words, if I can solve this, the tan of something is negative 1, if I can solve that, those will be my x-intercepts. All right, well, I already know that the tan of pi on 4 is equal to 1. So if I'm asking between here and here, the tan of what will be minus 1? Well, the related angle is pi on 4, except I want it in the second and the fourth quadrants. Now, if the related angle is pi on 4, 45 degrees, then what we want to do to find these other two angles is 180, or pi, minus pi on 4, and that will give us 3/4 of a pi, or 2 pi minus 1/4 of a pi, which will be 7/4 of pi. So I've put my quarters in here on the graph. 3/4 and 7/4 pi are my two x-intercepts. All right, so I've found intercepts. Now I probably, rather than looking at the sign to see where it's going up and down, I think it would be more useful to use calculus and actually look for my turning points and points of inflection, because then I can see exactly where the graph's going and where the high points and the low points are. So I'll make a little bit of room on the board here. Now, first thing I want to do is differentiate this thing. So let's find y dash so that we can find our turning points. So differentiating one part at a time, sine x differentiates to cos x differentiates to minus sine x. And if I want to let the first derivative equal 0, this will help me find my turning points. Now, letting this equal 0, I can see what sort of an equation I'd have. I'm going to add sine x to both sides. Now, if you want to write that first line down so it's really clear, go for it. If you can do that part in your head and jump straight to this part, that's fine too. Now, this is really similar to the last equation we just solved. If we divide both sides by cos x, we get tan x equals 1. And we've already thought about that. The related angle is pi on 4. So x would have to be pi on 4. And the other place where it's positive, the third quadrant, would be pi plus pi on 4. It would be 5 pi on 4. So these are our turning points. Now we need to ask two things. When x is either of these values, what's y? Because that way we can put them on our chart. And we also have to think about whether they're minimums there or maximums, so whether they're high points or low points. So first let's find the points. When x equals pi on 4, what's y? Well, it's going to be the sine of pi on 4 plus the cos of pi on 4. And both of these are exact values that we should know. What we have is the sine of 45 degrees, and you've probably remembered your exact values on a chart, and that's 1 over root 2. And then we have the exact same thing, 1 over root 2. Now, if you're adding 1 over root 2 plus another 1 over root 2, you get 2 over root 2. Can you simplify that further? Sure, it's bad practice to have surds in the denominator. Let's multiply top and bottom by root 2, and what we get is 2 root 2 over 2, which is just root 2. So we've got one point then, pi on 4 root 2, and now we have to have a look at our other one. Now, we can actually be a bit cheeky here. I'm just going to save some board space rather than writing this out again. If I've got 5 pi on 4, that's a related angle, isn't it? So if I'm finding the sine of 5 pi on 4, it's going to be really similar to the sine of pi on 4, except 5 pi on 4 is in the third quadrant, isn't it? And sine is negative there. So I'm going to have negative 1 on root 2. And if I'm finding the cos of 5 pi on 4, very similar to the cos of pi on 4, except it's in the third quadrant, also negative there. So this is going to be a negative. Now obviously for this second part, I'll write this all out below. I'm just saving board space here, being a little bit cheeky. So we've got minus 1 on root 2, minus 1 on root 2. We end up with minus root 2 instead of positive root 2. So our other point, 5 pi on 4 minus root 2. Okay, now if we're going to graph that, root 2, is that bigger than 1 or smaller? It's a little bit bigger, isn't it? So when x is pi on 4, y is root 2. And let's make that, say, up here somewhere. And that's a flat spot. So rather than a dot, you can put a little flat section and even label up here that this is root 2. And when we have 5 pi on 4, which is over here, we're going to have something similarly low as this one is high, and this will be minus root 2. Now it's very tempting to just say, look, we know the nature of this curve. This must be a maximum, and this must be a minimum because I've already got intercepts here and here. And in fact, it's one thing to do is to graph the curve in and then prove that these are maximums and minimums afterwards. You can do that. I'm going to actually just graph it in here now and then do my proof. Okay, and that's what I've got. I can label this point, pi on 4 root 2, and this point here, 5 pi on 4 minus root 2. Now, let's get to actually proving that this is a maximum and this is a minimum. Two ways we can do it. We've got our first derivative, so we could just check what the gradient is on either side of these, and perhaps that's the simplest thing to do. Or we could differentiate again and then sub in our values of x and check if we have a positive or a negative in our second derivative. I think I'll do that. Now, I would keep working down, but to save board space, I'm going to rub everything off back to here so that I can still see this. Because when I differentiate again, it's quite simple. Cos x differentiates to minus sin x, and sin x differentiates to cos x, so I have this. So now I just need to sub in my two values. When x equals pi on 4, y double dash equals, now the sine of pi on 4, that's 1 over root 2, but we need a negative out the front. And the cos of pi on 4, also 1 over root 2, so we get this. And we've already shown our working in previous lines to see that this is negative root 2. Now, a negative second derivative means it's got a frowny face. I literally just draw it like that. Therefore, it's a maximum turning point. I just write max TP at pi on 4 root 2. That's this one. Now we need to sub in when x equals 5 pi on 4. What would y double dash be? All right, 5 pi on 4. If we're finding the sine of that same angle, it's got the same actual value, doesn't it? But it's in the third quadrant. So it's going to be negative. So we've got negative 1 on root 2. That's just positive 1 on root 2. And similarly, cos of this angle that's in the third quadrant is also going to be negative. So we've got negative 1 on root 2. Again, it's a plus. So this one works out as root 2. And because that's positive, that's a smiley face, therefore it's a minimum turning point at that point there. I'm not going to bother writing it again, let's just point to it. So in my working, if I'm being thorough, I'd write all of that out. And we've just proven our points there. We could also prove a point of inflection here and here if we wanted to, or if we were unsure what the shape was doing. To do that, we need to let the second derivative equal 0. So let's go ahead and do that so that we're being really thorough. Let's let y double dash equal 0 to find points of inflection. All right, if we're letting this equal 0, I can imagine the equation with a 0 there. First thing I might do is add sin x to both sides. Now we've already solved this one before. We divided by cos x, and we got this. And we know the solutions to this one. We've already seen it. We've got this point here, 3 pi on 4, and we've got 7 pi on 4. So sure enough, we expected that these would be points of inflections as well as x-intercepts, and they are. Now, are we finished? Tempting to think so, but when you're finding a point of inflection, you can't just let second derivative equal 0 and solve for x. You have to check that there's actually a change in concavity on either side. So the way to do that, let's put a simple little table of values here, a table of concavities if you like. We need to put in our 2 points where we think there's a point of inflection so that we can prove that there actually is. Let's put a point that's on either side. So we could pick anything here. Let's pick pi on 2 and pi, or we could pick, doesn't really matter, we could pick this, 5 pi on 4, we could pick anything really, it doesn't matter too much, one of the points that's in between, and then 2 pi. And then we need to sub in, we know already that the second derivative is 0 here and here, so what we're looking for is a change in concavity. So plugging these in here, what we should get is a negative answer here because it's concave down. In between our points of inflection, it's concave up, should be positive, and over here it will be again negative, and we've actually shown a change in concavity. You can go through and do the actual working to prove what the second derivative is when x is any of those values, and you can choose values that make that working easy.